It
Yeah.
looks like one of the reactions is a Mozingo, which we didn't cover.
Yeah. Okay. So what we've been doing at this time slot in front of your laptop is an abbreviated version of what's going on. I could have sifted through every piece of information that's on the test and then picked out everything that wasn't exactly what we said in class. Or what I actually did is I picked some things out, the obvious things that I wasn't going to touch, but I left a few nuances in, like the Mozingo, which I haven't got to say Mozingo the way that I wanted to say Mozingo during class. Those are in the notes, and they are in the explanation of that reaction is in the already available lecture video that's on Blackboard. And in fact, when you get to the tail end of Organic 2, if you look at Blackboard, every topic at the end of Organic 2 actually has 3 videos. Because I've got 1 year where I did every single lecture recorded. We've got these ones, which is the more condensed version. And then there's another set where I did the lectures on a smaller whiteboard. And the camera on the smaller whiteboard is closer, but it was still to a live audience. So I've left that as your responsibility. It is a take-home test, therefore you're allowed to have to study a little bit. Now, having said that, you should be asking questions, and thank you for bringing it up, because we don't have much time left. Today technically is the last day of the term. If there is something about the remaining course material that you are not certain about, you should ask.
Okay, I guess then in that case, there's one more thing.
Yes.
I don't know if it's going to be the same where we should just kind of study up on it on our own, but I thought there was a question about the peptide chains and where they're going to break based on the reagent.
Yeah. That turns out to be a very easy test question. It's covered completely in the lecture notes. Selective hydrolysis, or which you're going to end up being called in biology restriction enzymes, where they snip at a specific position. That is in the notes, and at first glance it's a big daunting question because it's got a long string of characters, but that turns out to be a very, very simple question that is routinely one of the highest scoring questions on a test during a regular term.
Okay, thank you. I appreciate that.
Okay. Yeah, so going back to, we have a limited amount of time left. If you have something that you don't immediately get, ask for guidance. It's in the notes. It's in the video record. But ask.
I think one of the questions I had about the Mozingo was the reactant that I got before it had 2 sections where there were double bonds to oxygen, and I didn't know if the Mozingo would do both of them or if I did that question
Do the
wrong.
most reactive one. Aldehydes are more reactive than ketones. Ketones are more reactive than esters. Esters are more reactive than carboxylic acids.
Okay, so it'd be one of them, not
Last
both.
two are kind of the same. Yeah.
Okay.
Yeah, the Mozingo is like making an acetal or a ketal, but when it falls apart, it takes the oxygen with it. So it's a deoxygenation.
Okay.
And I like it. I like it because it's got a chemical that I used to use a lot, that ethane dithiol, which is the worst smelling chemical I've ever smelled. And it does something cute, and it's called Mozingo. And I like saying Mozingo. All right, that leaves us with a three-dimensional description of sugars. We really should be talking about amino acids and peptides. Not going to get to it. It's in the video record. It's in the lecture notes on Blackboard. There will be a very small number of questions about it. That's going to be on you. Let's get back to this. So, I have a Fischer projection. I have a aldehyde, a primary alcohol, chirality centers that are secondary alcohols, and I'm armed with the knowledge that aldehyde plus alcohol makes hemiacetal. So these alcohols, these two, are capable of being nucleophiles to that carbon and looping up. And remember, a hemiacetal has a carbon. I'm going to put a black dot on that carbon, carbon number 1, that is bonded to an alcohol and also bonded to an ether. So that carbon is bonded to oxygen 2 times. It's the only oxygen in the molecule, it's the only carbon in the molecule that is bonded to oxygen 2 times. Here, when it's an aldehyde, it's bonded to oxygen 2 times. When it's a hemiacetal, it's bonded to oxygen 2 times. All the other carbons are bonded to oxygen 1 time. Okay, that makes that carbon special. And when we are given the structure of a sugar in anything other than a Fischer projection, that's where we start. We're going to look at the shape of the molecule, and we're going to find the carbon that is bonded to oxygen 2 times. It's bonded to oxygen here and bonded to oxygen there. That position is called the anomeric carbon. The anomeric carbon for aldoses is always carbon number 1, because the aldehyde was at carbon number 1. Okay, what I'm going to do in the space that's underneath these diagrams now is to turn these Fischer projections into Haworth projections. Haworth, Haworth. And in doing that, I'm going to draw them this way. Six-membered rings are going to be drawn. Oh, no. I've drawn the 6s and the 5s on the wrong side. Hold on. Five-membered rings, the furanoses, look like this. You draw a pentagon, the oxygen is at 12 o'clock. Six-membered rings look like this. Hexagons that are on the side. We've gotten into the habit of writing hexagons on the point because we've been writing benzene and phenyl rings, which are typically on the point. These ones are going to be on the side. Now, we're going to go around the ring and look what the ring holds. This is carbon number 1 is in the ring. Carbon number 2 is in the ring. Carbon number 3 is in the ring. Carbon number 4 is in the ring. Then an oxygen. Carbon number 5 and 6 are not in the ring. So 1, 2, 3, and 4. I'm going to go around the ring clockwise. Similarly, when we do the 6-membered ring, it's going to be 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5 are in the ring. C6 is not in the ring. All right, here's how we translate a Haworth projection into a Fisher projection into a Haworth projection. Simple rule. If you point to the right of a Fisher projection, you will point down in a Haworth projection. So every carbon that goes around the ring has an up or a down attached to it. And if you were on the right hand side of the Fisher projection, I'm going to write you pointing down in the Haworth projection. So at carbon number 1, let's do it from left to right. I'm rolling over my documents that I've thrown on the floor. Okay, can everybody see this? All right, carbon number 1 on the extreme left furanose. The alcohol is to the left. That means it points up. The hydrogen is to the right. That means it points down. Moving to carbon number 2. The alcohol is on the right. That means it points down. The hydrogen is on the left, therefore it points up. Carbon number 3. The hydrogen is on the right. It points down. The alcohol is on the left, it points up. Then we get to carbon number 4. And carbon number 4 is where the ring meets the ether. And anything else that dangles off the ring, 5 and 6, carbons 5 and 6, those are typically drawn just pointing up. So here goes carbon 5, and there goes carbon 6. And this hydrogen, by convention, gets written in the down position regardless of what's going on here. It's these chirality centers that I have to show right here. Those are the ones that's important. Okay, if I look at this sketch, carbon 6 is the same, carbon 5 is the same, carbon 4 is the same, carbon 3 is the same, carbon 2 is the same, carbon 1 is different. Carbon 1 has the alcohol on the right hand side, which means it points down. But everything else is the same. So these two molecules differ only at carbon number 1. And carbon number 1 is the carbon that is bonded to oxygen 2 times. These two molecules differ in shape at the anomeric carbon. We call those anomers. And I wrote on the board at the bottom the word anomer. You really can't see that. I wrote it in pink, but it's being washed out. These are anomers. They differ in shape. The relationship between the alcohols, C1 to C2, is that in this molecule, they're cis to one another, and in this molecule, they're trans to one another. And in biochemistry, shape is absolutely everything. So this is important. So these two molecules have to have different names. If the alcohol group points upwards, it is the beta form. If the alcohol group points down, it is the alpha form. So I started with glucose. It turned out that it was D-glucose. Then I made them into a hemiacetal that was a 5-membered ring. So that glucose is now a furanose. So we would call it glucofuranose. It's still the D, and now I have a beta form and an alpha form. So the long name for this one is alpha D glucofuranose. Alpha D glucofuranose describes everything we need to know about the shape and the complete position of everything at every chirality center in this molecule. It tells me tells me what the relationship between the chirality centers is. Furanose tells me it's no longer in the aldehyde form. It's in a cyclic hemiacetal, which is a 5-membered ring. Ose, of course, tells me it's a sugar. D tells me that the bottommost chirality center is to the right. So I have this form. And the alpha tells me that of the two possible anomeric forms, I've got the one where the alcohol is pointing down. Okay, let's do that for the 6-membered rings. Same rules. Every carbon gets a group that points up and a group that points down. Let's look at the one here on the left. At carbon number 1, the alcohol is to the right. It points down. Carbon number 2, the alcohol is to the right. It points down. Carbon number 3, the alcohol is to the left. It points up. Carbon number 4, the alcohol is to the right. It points down. And then carbon number 5 is part of the ether into the ring. And by convention, we write whatever is hanging off the ring, now carbon 6, just pointing upwards. We don't put that group pointing down because it would conflict with what's in the ring. Okay? These two molecules are going to have everything be the same except what's going on at carbon number 1. Carbon number 1 is my anomeric carbon, because that's the carbon that's bonded to oxygen 2 times. It's the only carbon in this molecule that is bonded to oxygen 2 times. Alpha is down, beta is up. So this molecule right here is the beta, D, glucopyranose. Pyrans are 6-membered cyclic ethers. Furans are 5-membered cyclic ethers. All right, so we have completely filled a page with structures that we can generate just from one molecule. We're not quite done. If we're all comfortable with what we've got here, because I've run out of space, I'm going to draw what comes next above these two. Now, if you are a 5-membered ring, your internal angle is 108 degrees, which is not particularly far from the 109.4 degrees that is a perfect tetrahedral angle. So 5-membered rings are rigid. All of these groups of the 5-membered rings, those are all axial. They all point up or down from the ring because that ring is rigid. However, the internal angle in a hexagon is 120 degrees. But we know that sp3 carbons are going to demand an internal angle of 109.4. So hexagons are not planar, they are not rigid, they are puckered, and they waggle, and you thought perhaps that you would never have to draw chairs again, but you were mistaken, because these sugars exist in the chair form, and we write the oxygen here on the top right of the molecule where it sits. So the chair comes this way with that top right there. And now, what is up and what is down might be an equatorial, or it might be an axial. But the good news is we know how to predict whether a position is axial or equatorial based on whether the chair that we have drawn has a peak that is pointing down or comes to a peak that is pointing up. Remember, when two lines come to a vertex, if that vertex is pointing down, the axial points vertically down at that point. So what I have to do now is go around this molecule and put the alcohols and the hydrogens in positions that are either pointing up or pointing down to match what the Haworth projection is doing, and to reveal whether they are axial or equatorial. Okay. Starting at carbon number 1, the molecule that's on the left, the alcohol group is pointing down. Down at carbon number 1 is an axial position. Moving to carbon number 2, the alcohol is pointing down. Down at carbon number 2 is an equatorial position. Carbon number 3, the alcohol is pointing up. Up at carbon number 3 is an equatorial position. Carbon number 4, the alcohol is pointing down. Down at 4 is an equatorial position. 5 attaches carbon number 1 into the ring through the ether, so this is 5, and I'm going to write the substituent hanging off the ring, just pointing away. What I've drawn for this molecule, the alpha D glucopyranose, is going to be exactly the same as the beta D glucopyranose, except for the position, the configuration at the anomeric carbon. At the anomeric carbon here, the alcohol is pointing up, and up in this sketch is an equatorial position. Everything else is going to be the same. Okay. So, sugars are polyhydroxyaldehydes or polyhydroxyketones. If I have 6 carbons, and an aldehyde group. That generates 16 stereoisomers. One of them is glucose. That glucose exists in two forms. They're enantiomers, the D form and the L form. On this planet, it appears that only the D form is biologically relevant. So we've dismissed the L form of all of the sugars and realized that glucose, D-glucose, belongs in a series of D aldohexoses that contains a total of 8 stereoisomers. We then came to the realization that these straight chains probably don't exist naturally. Or they do, but they exist also in another form naturally, because aldehydes are reactive and they react with alcohols to make hemiacetals. And I have multiple alcohol groups inside my molecule. And because the aldehyde group is prochiral, every time I react an alcohol with it, it throws up either an R or an S. And so that one D-glucose that was part of a 16 sugar series itself generates 4 stereoisomers in its ring form. And they are the beta-glucofuranose, the alpha-glucofuranose, the alpha-glucopyranose, and the beta-glucopyranose. Now it turns out that one of these structures, one of those structures that's on the board, dominates. One of them is better than the others. Any guesses as to which of the cyclic structures that's on the board looks like a winner?
The alpha-glucopyranose.
That one.
Yes.
Okay. Any particular reason why that one looks like a winner?
Doesn't it have to do with
Is it the
position?
beta?
Ooh. Which one? I have 2 betas. I have that one's a beta.
The one right. That one, the one on the right.
This one.
Yes.
Okay. Why?
Well, when you're looking at it, they're all equatorial.
Remember all the way back. I know you don't want to remember chairs and boats, but if you cast your memory back a long, long way to cyclohexyl substituents, there was a definite benefit from having substituents be in the equatorial position. And that's equatorial, and that's equatorial, and that's equatorial, and that's equatorial. The beta pyranose is all equatorial. That's the winner. Glucose can exist, D-glucose can exist in any of these 4 forms. It's going to appear in this one more than the others because all of my substituents are equatorial. Now, Remember that if you have a ring structure, we typically don't show the hydrogens. Rings oftentimes don't show the hydrogens. This is how glucose is represented more in biochemical books than in chemistry books, because chemistry we typically want to see all of the bonding motif. But when this is just part of a bigger picture, I'm not going to put any more detail into this. If you see a chair and all the groups suspended from that chair are equatorial, that's a glucose. Okay? Let's look what we have. Come on. So, on the screen, we have the rundown of how to turn a Fisher projection into a loop, and then how to turn that loop into a chair. We just went through all of that. Here, on the second page from the notes, is what a ketose would look like. Now, ketoses don't have the luxury of, I'm going to have to make this a little, I'm going to have to zoom in on this at my end before I start scribbling on it. Ketoses don't have the luxury of having the anomeric carbon be carbon number 1. For fructose, the anomeric carbon is carbon number 2. That means that the carbon that is bonded to 2 oxygens in all of these Fisher projections and then into Haworth projections is not carbon number 1. So, when we're presented with something, I'm going to scribble on the Haworth projections at the bottom. When we're presented with a 3-dimensional structure of a sugar and we're asked to interpret it, the thing that you start with is to find the anomeric carbon. Right there. It is the carbon that is bonded to oxygen twice. That carbon is bonded to oxygen twice. The anomeric carbon used to be the carbonyl. When the molecule was in its straight chain, that's where the carbonyl was. And then that will lead you back to the Fisher projection, which will allow you to identify it from a list. Okay? So ketoses are a little bit more difficult to deal with than aldoses. Now, sugars exist naturally in multiple forms. The building block of a complex sugar is one of the small molecules that we've seen. It's a ribose or a lysose or a xylose or a ribulose or a fructose or a galactose or a gulose or a glucose or an allose or an altrose. Everything I've just said is a monosaccharide. It is a small self-contained polyhydroxyaldehyde or polyhydroxyketone. They themselves will accumulate into other small molecules that are larger than any of the individual monomer. So we're going to start with a monosaccharide, and then we're going to do a condensation. The condensation reaction is where you squeeze out a small molecule, and I'm going to highlight it right here. I have two sugars. They approach each other. If the two alcohol groups get close, then I can turn two alcohols into one ether. And now I have an ether linkage between the two groups. Okay? In this, I'm going to change it to a different color. In this ether linkage, right here, we look at the sugar on the left. We determine which carbon is generating the ether linkage on the carbon on the left. And when we look at the carbon on the left, it belongs to a glucose, and the ether is being made from the anomeric carbon, carbon number 1. And then it's going into the other molecule at carbon number 4. So this is a 1,4 linkage. But because every individual molecule already has a carbon number 1 and a carbon number 2 and a carbon number 3 and a carbon number 4 and a carbon number 5, possibly a carbon number 6. This is not a 1 to 4 linkage. It's 1 out of one molecule and 4 into a different molecule. So I cannot use the number 4. It's already taken. This has to be 4 prime. Using the prime, the little apostrophe after a number, tells me it's in a different subunit. So now I know what the numbers between the two carbons in this linkage is. I also have to tell you whether that linkage is pointing up or pointing down out of the sugar on the left. And if we look, the ether is being formed on an alcohol that is pointing up in an equatorial position from the sugar on the left, and up at the anomeric position is a beta. Betas are up, alphas are down. Okay? So, two glucoses that are joined together by a beta 1,4 prime glycosidic linkage make a maltose. And anything other than that is going to make a different named sugar. And anything that you can think of or find in your food labeling that ends in ose is a sugar. And some of the little disaccharides like sucrose, that's the big one, the white granulated table sugar. That is a glucose and a fructose. And that's an alpha linkage out of the glucose into the fructose. It's pointing down. Those disaccharides conglomerate into making oligosaccharides, and then they conglomerate to make big complex carbohydrates called polysaccharides. And when we look at the world of polysaccharides, there's several different forms of both of these, but the two big ones for glucose are cellulose and starch. And when we look at cellulose, cellulose is this beautiful long chain of glucoses, all linked together with beta 1 4' glycosidic ether linkages. And then you look at starch, and starch is a little bit more clunky because the glycosidic linkage out of one glucose and into the other is an alpha 1 to 4' linkage. It comes out of the bottom of the left-handed glucose and into the second. So these are the two forms of glucose that we find most abundant in nature. There are others. There's different types of starches specifically. But glucose is a fiber because it's a long chain. And starch, well, starch looks like it could set itself up as a fiber, but it also does this thing where it turns into like a globule. And it turns out that humans, if we're what we suspect that we are, the highest form of life on this planet, that's what we suspect that we are, then why is it that of the two forms of glucose-based complex carbohydrate that's out there, why is it that we only have the metabolism for starch and not the metabolism for cellulose? Cellulose is the fiber that plants use for structure. So cellulose is the long, stringy fiber in grass. And humans can't digest grass. Whereas starch is the globular complex carbohydrate in potatoes. And potatoes are yummy. They're clearly a gift to us from nature. If we look at those two molecules and we know that the glucose should be in the beta form, and yet we can only digest the one that's in the alpha form, that screams that there's something wrong. Only it turns out, right at the bottom of the page, that there isn't something wrong. When a sugar is an independent unit, the beta form is the most stable. Here we go. This. The circle in blue at the bottom. That's a glucose, and I've put the substituents on the anomeric carbon into an equatorial position. But something happens when I turn that alcohol into an ether. When I turn my glucose into a glycoside by putting this R group in place of where the H was. That R group pushes electrons, which inflates the lone pair of electrons on that oxygen, which repels. And so the better form for a glycoside is the alpha form. This is something that's become known as the anomeric effect. That sugars, when they're independent, want to be in the beta form, specifically glucose. Glucose, when it's independent, wants to be in its beta form. But when you put it into a chain, it wants to be in the alpha form. Okay. All right. That pretty much is the end of sugars. If you look at your test, it's probably the last question. If you look at the study guide that's up there or any of the previous tests, the last page is, here are some depictions of disaccharides. And then I have a table, and that table tells me, here are all the names of all the possible sugars you can get. And there are hundreds of named sugars out there, because that's the hole that we've dug for ourselves. But with every name there comes a description, and it will say this is a glucose and a galactose, and it's an alpha 1 to 3 prime. The question that is being asked of you is easier to do than it looks. You have two things to figure out. Are the components that I'm looking at in my disaccharide, are they glucoses? That's a yes or a no question. And we know how to recognize glucoses. And if they are glucoses, where's it coming from and where's it going? Is it alpha? Is it beta? Is it 1? Is it 2? Is it 4 prime? Is it 3 prime? What is it? Is the linkage coming up or is it going down? And by process of elimination, you can figure out how to answer that question. Okay? The remainder... Oh, what happened there? Hold on. Come on. Oh, I just closed you. The remainder of the material in a regular term would be this. We would describe lipids. Lipids are glycerols and fatty acids. We would describe terpenes. Terpenes are hydrocarbons. No, they're not always hydrocarbons. They're simple molecules that have repeating 5 carbon units in them. They have a distinctive shape. Part of the terpene system are steroids. We would have a very quick look at DNA. And, oh yeah, look, that's polymers right there. And then we would be done. Missing from this is my amino acids. The other notes on Blackboard somewhere, amino acids. You have an amine at one end, a carboxylic acid at the other end. You have a chirality center in the middle that's holding on to a side chain. That side chain, someone's going to want you to memorize the names of all the amino acids that have different side chains. Not me. I want you to be able to pull one out of a hat based on, is that side chain polar, non-polar, acidic, or basic. It's in the notes, it's in the previous videos. If you give yourself 45 minutes to watch the previous video and read the notes, you can answer anything that I'm ever going to throw at you in terms of a question for that. Okay, and with that, our time is up. It's been a strange term. It was set to be a really good one. I had said previously, early on, As a group, you are the highest scoring, highest performing group of students that I've had the pleasure to teach organic chemistry to in, 6 or 7 years. You've been really good. It would have been optimal if we could have just plowed on and continued as we were, but hey, strange things happen. Good luck to you all. Don't forget to ask for help. Okay? And I'll see you all next academic year.
I have a question.
Yeah.
Okay, so on the terraformations, I know that when we were writing them and drawing them, we were going around like counterclockwise, counting them, like the carbon 1, 2, and 3. But on here, when we're identifying them, we're going around clockwise. Yeah, so do you always have to go clockwise, or can you go...
Yeah, it's a convention that oxygen is in this position.
Okay.
That's a convention.
Okay.
Now, if okay, so the convention of showing you the molecule is this way, with the oxygen here in the top right. But if an exam question comes along and says, what is this? I'm not particularly likely to do that to you. But if a question like that arises, you have to find a way to put it this way, and you have to identify the anomeric carbon. The anomeric carbon is this one. First thing that you have to do. Once you identify the anomeric carbon, you're pretty much set.
Okay, got it. Thank you.
So, yes, some of the questions where we're going to ask you, what is this disaccharide? Instead of them just being stuck this way, sometimes you get them kind of stuck a different way.
Yeah.
Okay.
Okay, that's just what I was wondering.
Find the anomeric carbon.
Okay.
Find the carbon that's bonded to two other carbons, two other oxygens.
Alrighty, thank you.
Yeah.
Bye, Dr. McGuire. Thank you for a great 2 semesters. I appreciate how passionate of a teacher that you are.
Thank you. Thank you. It's been fun. It's been fun. It's been an adventure.
I'll see you next term.
Yeah. Good luck to everybody.